Welcome, first-year chemistry students. Let's kick off today's explainer. I want you to take whatever preconceived notions you have about chemistry. You know, the idea that it always ends in some boring, uniform, completely still equilibrium, and just throw them right out the window. Today, we're exploring a side of chemistry that is vibrant, highly dynamic, and honestly, downright beautiful. We are talking about chemical self-organization and Turing patterns. Okay, let's dive into this. How exactly does a leopard get its spots? Or a zebra, its stripes? What about a tropical fish and its incredibly intricate, maze-like patterns? Well, for a long time, this was strictly a biological mystery. But today, we're going to bridge the gap between biology and chemistry and see how the very paints nature uses to color the animal kingdom are actually driven by fundamental chemical reactions. To really get this, we have to define a biological term: morphogenesis. Essentially, this is the selective cellular development process where incredibly complex patterns self-organize out of very simple physical laws. Now, here's a totally crucial point for us as chemists. This organization doesn't happen at thermodynamic equilibrium. It operates far from it. It forms what the Nobel laureate Ilya Prigogine called dissipative structures. Basically, these are systems that maintain their complex order by constantly exchanging matter and energy with their environment. And the person who first cracked the mathematical code behind this wasn't just a biologist or a chemist. It was Alan Turing. Yeah, the legendary computer scientist and codebreaker himself. In 1952, just 2 years before his death, he published a groundbreaking paper called The Chemical Basis of Morphogenesis. Turing hypothesized that biological patterns could literally be explained by a reaction-diffusion system. In simple terms, chemicals reacting with each other while simultaneously spurting out. Section 1. The activator-inhibitor model. So, to see how Turing's math actually works in the real world, we need to understand the engine driving these reactions. In this model, you have this constant battle between two chemical species. On one side, we have the activator. It's autocatalytic, meaning it triggers its own production, which causes its concentration to build up locally. Think of it kind of like a brush fire. Then, on the other side, we have the inhibitor. Its entire job is to suppress the activator to put out the fire. But here is the secret sauce. The inhibitor has to diffuse through the solution way faster than the activator. It's like a sprinkler system that kicks on and rapidly sprays water far beyond the initial flames. It prevents the fire from spreading everywhere, but it allows localized pockets of fire to keep burning. And this brilliantly illustrates the concept of diffusion-driven instability. You have your activator building up tightly in one specific spot because it diffuses so slowly. Meanwhile, the inhibitor, which is actually produced by the activator, spreads out much more rapidly. In our mathematical models, we express this as the diffusion coefficient of the inhibitor being strictly greater than the activator, or dy is greater than dx. This condition is the absolute mathematical requirement for Turing patterns to emerge, no way around it. Now, I know some of you are probably stressing about your thermodynamics lectures right about now. You might be thinking, wait a second, spontaneous order? Doesn't that directly violate the second law of thermodynamics? Let me reassure you, it absolutely does not. While the system breaks symmetry and creates localized order, those beautiful spots and stripes, it is continuously dissipating energy to do so. The overall global entropy of the universe is still increasing. Your thermodynamics exams are totally safe, I promise. Section 2, Proving It, the CDIMA reaction. For about 40 years after Turing proposed this, it was just an abstract mathematical theory. Chemists struggled to prove it in the lab because getting two molecules to have vastly different diffusion rates in an aqueous solution is notoriously tricky. But that all changed with the CDIMA reaction. This stands for chlorine dioxide, iodine, and malonic acid. These are the core components of a specialized chemical oscillator. But unlike older oscillating reactions, like the famous Belousov-Zhabotinsky reaction, which gives you moving target patterns, the CDIMA reaction actually lets us observe true, stationary Turing patterns, the exact stable spots and stripes Turing predicted. And the secret to making the whole shebang work? It lies in a super common household ingredient: starch. Right, before we get to the starch, let's explicitly assign our chemical roles in the CDMR reaction. Iodide acts as our activator. It actually disfavors its own consumption in an autoinhibitory reaction, effectively acting to keep its own concentrations high. Chloride, on the flip side, is our inhibitor because it aggressively consumes the iodide. So where does starch come in?
Well, starch is historically used as a color indicator, right? It turns dark blue when iodine is around. But in the CDMAR reaction, it does something almost magical. It binds reversibly to the iodide ions. Because starch is this massive macromolecule, it acts like a pair of heavy boots on the iodide, artificially slowing down the activator's diffusion rate. This accidental, totally brilliant addition is what finally satisfied Turing's crucial mathematical condition, making the inhibitor diffuse faster than the activator.
Section 3. Controlling patterns with light. Once chemists had a working model, they didn't just want to stare at it, they wanted to control it. You see, the CDMA reaction is highly photosensitive. When you strike the reaction with visible light, it causes the photodissociation of the molecular iodine, which generates radical iodine atoms. These radicals then kickstart a chain reaction that produces more of the inhibitor, chlorite, while simultaneously chewing up our activator, iodide. Essentially, by shining a light on it, you're handing a massive advantage to the inhibitor, which effectively suppresses the formation of the Turing patterns entirely. Now, what's really interesting about this slide is what happens when you don't just flood the dish with light, but instead use spatial light gradients. By projecting specific light patterns onto the chemical dish, we can actually force the reaction into breathtaking, complex new morphologies. By carefully controlling that balance of the activator and inhibitor with light, chemists have coaxed out square lattices, oscillating waves, and these highly unnatural engineered geometries. It's essentially chemical lithography. Section 4. Identifying the chemical roles. So you've seen the theory, the chemistry, and the visual proof. But as future analytical chemists, you guys need to know how to look at a brand new, unknown reaction and figure out exactly who is playing what role. To identify activators and inhibitors experimentally, classical kinetics, the kind you usually learn in your first semester, often fails us. Classical integration methods tend to ignore the rate of product formation over time. To solve this, we have to use the method of differential reaction orders, where we compare the initial reaction order to the final reaction order as the products begin to accumulate and interfere. Let's walk through this table because this is the real practical takeaway you can use in the lab. We measure the initial reaction order, let's call it Ni, right at the start. Then we measure the final order, Nf, as the reaction progresses. If Ni is less than Nf, it means the products being formed are actually speeding up the consumption of reactants. It's autocatalytic. Boom, you found your activator. Conversely, if Ni is greater than Nf, the product is suppressing the reaction, which identifies it as your inhibitor. It's a beautifully simple, mathematically rigorous way to map out complex reaction dynamics. We've covered a ton of ground today, from the brilliant math of Alan Turing to the fascinating photosensitivity of the CD-Markinander reaction. I want to leave you with a provocative thought here. Chemistry is not just about clear liquids reaching a dead equilibrium in a beaker. It is the dynamic, self-organizing engine that paints the living world. So the next time you see a zebra or a leopard or a beautifully patterned fish, I want you to ask yourself, what are the chemicals doing? Keep questioning, keep observing, and I'll catch you in the next explainer.